A mole can be 6.022 times 10 to the 23rd of anything. Sometimes, rather than reporting the moles of individual ions from a salt in solution, we can use moles to report how many positive or negative charges are in the solution. The number of moles of positive or negative charge are referred to as equivalents. When you use equivalents, be sure to keep the positive or cationic equivalents separate from the negative or anionic equivalents. Because some ions have charges that are greater than 1, the moles of ion in a salt may not always equal the number of equivalents, or moles of charge, that ion contributes in solution. For example, magnesium chloride. It contains a ratio of 1 magnesium to 2 chloride ions. This tells us that 1 mole of the salt will contain 1 mole of magnesium ion. But magnesium has a charge of +2 for each ion. So 1 mole of magnesium chloride actually contributes 2 equivalents of cationic charge from the magnesium. Similarly, to measure the anionic equivalents provided by magnesium chloride, we note that 1 mole of the salt, again 1 mole of magnesium chloride, provides 2 moles of chloride, each ion containing a charge of -1. So 1 mole of the magnesium chloride salt will provide 2 equivalents of anionic charge from the chloride. We use the equivalents per mole as a conversion factor in our calculations. And so a shorthand way to remember how to determine a salt's equivalents per mole is to pick either the cation or the anion, not both, just one, and we multiply the ion subscript, which is the number of moles of the ion in the salt, and multiply it by its superscript, which is the amount of charge that ion contributes. So in magnesium chloride, we could look at the chloride half of the salt and say, well, it has a subscript of 2, and the chloride, each chloride has a charge of -1, and so 2 times -1 is, well, absolute value is 2 equivalents per mole. Or you could look at the magnesium side and say there's subscript of 1, charge of 2, 1 times 2 is 2 equivalents per mole. For neutral salts, in which the positive charges balance the negative charges, like magnesium chloride, the number of cation equivalents will always be the same as the number of anion equivalents. So you can use either the cation or the anion to calculate equivalents per mole for the salt. But again, don't try to do anything fancy like add them together, subtract them from one another, or anything like that. Just use one or the other to derive the conversion factor. Okay, in the first example, it asks how many equivalents per mole are provided by calcium citrate. So calcium has a charge of +2, citrate has a charge of +3. We don't know what the subscripts are until we crisscross. And then we get calcium 3, citrate 2. And then we can use either the cation, subscript 3 times superscript 2 gives 6 equivalents per mole, or we can use the citrate side. 2 citrates times their charge of 3 each gives 6 equivalents per mole. Either way, you get 6 equivalents per mole, which is going to be true for any neutral salt, and most of them are neutral. How many equivalents of calcium would be provided by 0.08 moles of calcium citrate? So this is where we can use our conversion factor, 6 equivalents per mole, and we want to know how many equivalents are provided by 0.08 moles. Chris, don't need to cross. 0.08 times 6, that's 0.48 equivalents from 0.08 moles. How many equivalents of calcium would be provided by 1 gram of calcium citrate. So this has 2 steps in it. So our conversion factor is in equivalents per mole, and we're provided with grams. And so we have to get grams to moles first. And that involves using molecular weight as the conversion factor. And we've already determined what the formula is for calcium citrate. So 3 times an atomic weight of 40 for calcium, plus 2 times the molecular weight of 189 for citrate is 498 grams per mole. So our first proportion will be to use that molecular weight, 498 grams per mole, to determine how many moles are provided by 1 gram of the salt. So crisscross and divide by 498, and it's a small number. It's 0.002 moles. But we can now put that into a second proportion where we can determine the number of equivalents in 0.002 moles using the conversion factor, 6 equivalents for every mole. 6 times 0.002 tells us that there are 0.012 equivalents provided by 1 gram of calcium citrate. Finally, what's the normality? Normality is capital N, and it's equivalents per liter. It's similar to molarity. So what's the normality of 1 gram of calcium citrate dissolved in 2 liters of total solution? So we know that we're going to put 2 liters down here, and then the question is, how many equivalents is 1 gram of calcium citrate? Well, by golly, we already calculated that up here. 1 gram of calcium citrate we figured was 0.012 equivalents. So 1 gram is 0.012 equivalents. We put that up here. We put the 2 liters down here on the bottom. We divide, and that is 0.006 equivalents per liter, or a 0.006 normal solution. All right, the next slide has problems for you to try. Go ahead and see if you can do them, and I'll have worked out examples in the next video.